Hey folks, so today we're going to be taking a look at how to model specific functions for constraints. Essentially, we're going to be using Microsoft C3 to take some C code that has lots of constraints, and we're going to format those and model those for Z3 and ask for a solution. There's a couple different ways that you can solve this, and this really came to mind about 7 months ago when I saw this post on the subreddit exploit dev. So the user asks, basically, I have this piece of code. Is there an easy way to reverse engineer this so that we get a specific string? They knew that there was only one string that satisfied all the constraints for this, and they wanted to figure out what's the best way to do this. And looking at this and scrolling down and seeing all of this, first of all, like my brain just gave up on trying to do this with pen and paper. There's no way I'm going to try to do this. I think some people would do it, and maybe it's a very interesting exercise. This just looks daunting to me. I think another way, and this is the two kind of top posts here, and mine is down here, is use a theorem prover, use something like Z3, but that could be more work because easy is really kind of relative. Like how hard is it to really model those constraints to pose to Z3 so that it can answer those solutions for you? I think that really depends on whether or not you're using like the Python API for it, or if you're using SMT-lib. Do you know how all that stuff works and how to present it to it? In this particular case, it's really nice because it's really well suited for this. Another way that we can solve this is to give it to a symbolic executor. So we can use something like anger. We can take the code, compile it to C, and then present it to anger, give it a starting point where it's going to load the binary, and then give it the exit point and have it solve for that. But what it's doing is collecting all of those constraints, and under the hood, it's just passing all of those to Z3 anyway. So it'd be really nice if we can kind of peek under the hood and take a look at what it looks like to format this. I personally don't know SMT-lib, which is sort of like the true way to pass things to Z3 in basically any modern theorem prover. So I'm not going to be using that. It's a little like Lisp-like, and honestly, it intimidates the crap out of me. But we'll be using the Python bindings for this. So this is what it ends up looking like. I have a solution here. I love this because sometimes I try to answer questions just to see if I really know what I'm talking about. So I tried this and I had trouble getting it work. That this is my solution. And I was giving these essentially 8 bits instead of like 32 or 64. And the way that I was doing this with bit vectors, it wasn't actually working. And all I had to do was just turn those bit vectors into 32 or 64, and it ended up working. So that's a mistake that I feel like I'm not going to make in the future. Or if I do, then I'll be able to lean back on this experience and just solve that kind of right away, or fix that problem right away. And I think it took me probably like 30 minutes of just kind of thinking around, reading at approaches, and then finally trying that to get it. So I like these types of exercises, so I wanted to share with you. So what we have is, this is the original challenge text, and looking at char at and the way that this is formatted, I think this was originally posed as Java. So I basically just converted it. I'll put this up in a gist so people can grab it if you wanted to. And then just kind of wrapped it with the main function. It was just this function here. And the only reason why I want to do this is because I want to be able to, yes, the password on this is password. I want to be able to run this and then prove that my input that's solved by Z3 actually works, right? Okay. So the way that this is going to end up happening is we're going to compile this. We're going to check to make sure that we have a valid input. We'll pass that right to check, and then check is going to be the thing that has all these constraints. First of all, the first constraint is if the string length of the input isn't 15, then we're going to bail right away. So we know that our constraints are 15. This is really important to scoping the solve time for this and modeling the problem in the first place. It makes it kind of easy, but we can explore things in future videos and how to do more complex situations with loops and things like that. So right now, we're basically just going to the very first character and putting it into a variable named a, which is an integer. And we do that for all 15 characters for a through o. And then each of those characters, there's some mathematical operations that are performed, and they must equal a specific output. The problem is this j appears here, but then if you go down, it also appears here, and it also appears here, and it also appears here. So doing this means that even if you find a j, an h, a k, and an a that all satisfy this inequality here, then you're going to have a huge problem because you don't know if those particular inputs or those things that you've chosen are going to satisfy other ones that you see down the road. So it actually becomes kind of a nightmare. And solving this through brute force means that, like, oh man, this takes so long to try to find something that work. And it turns out, and this is provable, that there's actually only one input that will satisfy this. So you can probably fuzz a 15 input character um, until like the heat death of the universe. I don't know how long it would actually take, but it's a lot longer than I want to spend doing it. So we have to try to model this and figure out what's the best way to present this to something like Z3, and I've done that here. So first of all, we'll install Z3. Z3 requires the Python bindings and then also compiling a library. So if you do this with pip install, I'm going to do it on Linux just because I had all the build chain and everything set up to just get everything compiled and ready to go. What you can do is I'll just import Z3. You can do import Z3 as star, so you can just get access to these things. I like to keep things separate, so like just importing everything. So we'll use bit vectors. When you look at SMT solvers are reaching out to various SAT solvers or satisfiability modular theory is what SMT is, and we're using satisfiability and different strategies for solving really hard problems like NP-complete problems. So what it's doing is we're going to be using a theory of bit vectors. We can use integers. There's other things that we can use too. There's basically SMT is like a toolbox that you can open up and grab different tools for solving really hard problems. And one of the ones that I want to leverage is a bit vector. I like doing bit vectors because it means that we don't necessarily have to worry too much on if there's like a floating point, or if we're looking at an integer or something like that. We can just say, listen, I have something that's represented as this many bits. Go solve it, and then at the end I can go ahead and ask for a conversion in a different form if I need to. So what we'll do is I'm going to create Python variables A through O, and then I'm going to name them. So the way that I'll reference them in the model is also calling them A through O. So Python's variable for A is A, but I've also called inside of the state for Z3, that variable's name is also A. It could be puppy A and jellybeans 3 or whatever. It doesn't matter. And then this bit vector is also going to take a width. So this could be 8 bits, which didn't work previously. It could be 32 bits, 64 bits, 128, whatever you need to, right? But we need to keep in mind that when we're doing computations with this, we're posing things to Z3, we need to compare apples to apples. So sometimes if you have something that's 8 bits, you might actually need to extend that to be to 32 if you're like doing an operation on two different things. They need to be essentially the same width. So then what we'll do is create a solver instance. So S is going to be our solver, and then we're going to add constraints. So we have all of these things, and all I'm saying is, listen, it's something this wide, and there are 15 of those. I don't know what bits are set in that, but you need to figure that out. So when we come here, we can say, all right, I want you to set, I want to add this constraint to the solver, and the constraint is that I want A to be greater than or equal to 32, but less than or equal to 126. Where does this come from? Well, I know that the inputs is going to be a string, right? So if I go to an ASCII table, images, here we go. What I'm looking at is I'm basically saying I want it to be like spaces, include that, and then go all the way down here to like the tilde and do 126. So anything between here, so this means pluses, stars, ampersands, if I knew that the input did not include any of these things, I can further constrain this more to say, or if I know the input's only capital letters, I can go just 65 through 90, and we can constrain it even further. Typically, the more constraints that you can give, the faster of solution that you'll get. But it really depends on the problem, right? So I'm going to do this for every single character, right? So all of these 15 characters are going to have that same constraint imposed on it. After this, there's a really nice way that we can just add these directly to Z3. So if I take a look at what the original talents text was, or my converted C, let me see. Open this up. Get that. Push this over here. Okay, wonderful. So here is my adding this first equation here. Okay. The same thing. I literally just copy and paste it out. When I get to things like this, where this Q, that space up there, or this greater than, I'm just going to convert it to a number. Okay, so rather than using the actual character there, do that. So I've posed all of these things. Now I can say check, right? Which is going to ask Z3, considering all the constraints that I've given you so far, can you prove that there's a satisfiable model for that? And this .r just gives us the output in sort of like a raw form, so I can check 0 or 1 instead of actually checking for sat or unsat. Um, you don't have to do that, just a thing. From that point, if it checks it and says, yes, this is satisfiable, or no, this is not satisfiable, we have different options. For satisfiable models or constraints that we've posed, we can say .model, and it'll give us one input that solves that, right? From there, I have to go, I'm going to create an empty string. I'm going to go to each one of those characters or those variables that I have. And I'm going to say in the model, go ahead and give me the A case, right? And then I want you to give it to me as a long. Then I'm going to convert that to a character, and the character representation for that will fall within the ASCII range. And then it'll be printed out in a solution. So let's see what that looks like and how long it takes. Keep in mind, try to think about how long this might take you to actually fuzz this. It's kind of crazy. So let's do Python 3 solve. I already have everything set up, and that's it. That fast, we've solved all of these inputs, and this is what it came out as. And as we took each one of these, so if we took A, for example, it was 79, and then B was 102, it comes out in a random order, and then we take those and put them together, and it turns out to be Sound of London. So let me clear this, and then do challenge. Just make sure this is right, okay? And then we'll give it Sound of London. And yes, you found the correct input. If I do anything else, it's going to say, sorry, it's wrong. So there is literally only one thing. How can we be so sure that there is only one input? Well, what we can do is we can actually further constrain this after we do the initial check and getting the model. So now that we've done this once, we can come back around and say A will no longer be what it was previously in the model. And then I can say B, I don't want that to be exactly what it was in the last model. So we basically remove Sound of London as being an actual viable constraint, just like we put all of these constraints in here or these. And when we feed it back into the solver and we say, try to find me a model, it goes, okay, well, it can't be Sound of London. Let me try something else. And it'll exhaust all possible the search space for that and basically say, this isn't solvable or it's unsat, which is really cool. So you can, if you have something like a checksum and you need to generate valid input that matches that checksum, you could fuzz it, hoping that you find, and every once in a while you'll get something that generates like a valid checksum. We're not talking about cryptographic hashes, just checksums. So it's like taking the characters, adding them together, and like subtracting one or something like that. So these types of things end up being solvable really fast. So what you'll see is like if you take a look at a checksum, and we'll do this in a future video, is you can generate things, inputs that satisfy the checksum as fast as you can if you were just fuzzing. It is insane how quick this can be. And it's really exciting and kind of fun to do. So the question you might have is, if I'm looking inside of my disassembler or decompiler and I have this type of thing, how do I take like raw MIPS instructions and then convert them into this? There are ways and strategies to do that. Personally, I think it'd be best to do it on an IL, so lift it up to Binary Ninja Intermediate Language or Ghidra P code, and then take things from that to try to formulate those. But you can automate that process. I think at that point, it's probably best to try to load it into a symbolic executor that can collect those things, format it for you, and then feed it to Z3 to get outputs. But I think this is a really interesting exercise. I'll put all of these challenge files up here so that you can play with this yourself if you want on GitHub. Other than that, thanks for watching.